So here, anisole undergoes nitration 10,000 times faster than benzene and 400 times faster than toluene. And we just said earlier, the alkyl group can donate electron density. It stabilizes the sigma complex. But here we have a electronegative element, oxygen. So this seems counterintuitive. So we can be curious about that. The result seems curious because oxygen is strongly electronegative, but somehow it donates electron density to stabilize the transition state and the sigma complex. Of course, what's missing is those unshared pairs of electrons on oxygen. So nitronium electrophile comes by, these electrons grab it. Right there is our tertiary carbocation. And then these electrons can jump down, delocalizing the positive charge there. Of course, we can move that bond over there, move that bond over there. So we can really delocalize that positive charge in a tertiary carbocation position. And the book tells you this is especially stable. Resonance stabilization is provided by a pi electron between the methoxy substituent and the ring. So there's the pi bond, and you can see how they're all conjugated. Normally I wouldn't say putting a positive charge on oxygen is a stable thing, but you know, the hydronium ion, we see it all the time. Now if we try and do the meta position, put it on there, there's our carbocation, move that pi bond over there, move that pi bond over there, and we never get that positive charge in a position where those electrons can jump down and stabilize it. These resonance forms show that the methoxy group can never stabilize the sigma complex if the electrophile hits in the meta position. Here's bromination. And so this thing we say is strongly activating. We just saw 10,000 times more activating than benzene alone, 400 more times than toluene. So notice no ferric bromide catalyst. It just goes. And let's get aniline, lone pair of electrons, not as electronegative as oxygen. And so it's very active by that double bond, by the lone pair being able to form a double bond in a very similar fashion. I guess they add some baking soda, neutralize the HBr that gets formed. So now we've seen some things here. Too bad we don't have benzene by itself. So here's an alky benzene. Anilides are even more reactive. There you see the double bond. And you can imagine you're going to get a big pi system in the transition state in the sigma complex. Here would be an ether, a phenol, anilides, and looks like a deprotonated phenol. So in general, we say if we have a electron donating group, we say the ring is activated, and it gets activated in the ortho and para positions. If we have an electron withdrawing group, the ring gets deactivated in those positions, and the only place you can do aromatic electrophilic substitution is in the meta position. The substituent on the ring is electron donating. The ortho and para positions will be activated. Likewise, if the group is electron withdrawing, the ortho and para positions are deactivated. And the net result is if substitution occurs, it occurs in the meta position. So here's a nitrobenzene, and we decide we want to put another nitro group on it. We might have to work on it pretty hard. This is a pretty hot temperature. It's pretty harsh conditions, but that nitronium ion goes on there, and look, 93% shows up in the meta position. Electrophilic substitution reactions for nitrobenzene are 100,000 times slower than benzene alone. So this is deactivating the ring. Saw that deactivators shut off those positions, and we see the meta position there. So slight mixture, but mostly meta, only small amounts of those other two. So what's going on? To answer these questions for all of these, we write resonance structure. Let's imagine our electrophile going on in the ortho position. So we saw the other day, this thing we write NO2 and it's electrically neutral. But if you do the Lewis structure, you're going to have something like this. Of course, you can put the negative charge over there. So a resonance hybrid. See how you always have a partial positive charge on nitrogen, and when you put the electrophile there, you have a positive, and like charges repel each other. Nature's not happy with that. Of course, there's the other resonance structures. The nitro group is a strongly deactivating group. When considering its resonance form, the nitrogen always has a formal positive charge. Ortho or para will create this unstable intermediate. All right, so let's go and put it in the meta position. These jump out. I'm gonna put a positive charge right there. Move those bonds over, puts the positive charge there. Move those electrons over, puts the positive charge there. So in the meta position, we never get a positive charge here close to the other positive charge. And that's why we get the meta product. Meta substitution will not put the positive charge on the same carbon that bears the nitro group. Here's our potential energy diagram. So here's benzene, and so this is why it's 100,000 times slower, larger energy barrier. And look at this large energy barrier, that's why we saw like 6% and 0.7%, the ortho and para. And once again, nature doesn't like to put a positive charge there when you have a formal positive charge on that nitrogen. So you want to recognize groups and what they're going to direct. Most electron withdrawing groups are deactivators and meta-directors. The atom attached to the aromatic ring has a positive or partial positive charge. Electron density is withdrawn inductively along the sigma bond, so the ring has less electron density than benzene, and thus is slower to react. It's the electrons that grab an electrophile. So here's acetophenone. Oxygen's electronegative. So possibly from other topics in the course, you know that nucleophiles like to hit here because this thing's an electrophile due to the polarization of that bond. So it's similar to the nitrogen on the nitro group. This thing hits here in an ortho position, puts the positive charge there. Nature doesn't like that. And if we drew all the resonance forms, when I didn't do the PowerPoint, I'd draw all these. I was about tired of them by that point. In the ortho and para substitution of acetophenone, one of the carbon atoms bearing the positive charge is the carbon attached to the partial positively charged carbonyl carbon. Nature doesn't like that because like charges repel. This close proximity of the two positive charge is especially unstable, gives it a very high energy of activation, and so we don't see those products. So we predict this is a meta-director. These electrons grab the electrophile when it's in the meta position, puts a positive charge there, move that bond over, puts it there, move that bond over, puts it there. So a carbonyl carbon is a meta-director. It avoids putting a positive charge right there when carbonyl carbon has a positive charge. So these are all deactivators. We saw a little bit earlier, we had a slide with a bunch of activators. So nitro, Lewis structure gives you that positive charge. Sulfonic acid, we looked at how SO3 adds to a benzene ring. Then if you put some water, you get the sulfonic acid. Once that's on the ring, you can draw these resonance structures and you see a positive charge. So this is going to be a deactivator. Cyanide, I wouldn't think this so much, but those electrons can jump over there, putting a positive charge. We looked at acetophenone, and of course a corresponding ester, or a quaternary ammonium salt. That's what we would call this thing. Tetramethyl aniline iodide. So think ammonium cation, N with the 4 H's. We can have N with 4 alkyl groups, and we get the same thing going on there. So halogens, they're electronegative. So I like to think this is kind of like the anisole. We still get ortho and para, but it's a deactivator. Halogens are deactivators since they react slower than benzene. That's just what we observe. We can probably chalk it up to it being electronegative. Sucks the electron density out of here. It's harder for those electrons to grab an electrophile. However, halogens are ortho-para directors because the halogen can stabilize the sigma complex, and that's due to all those lone pair electrons. So here, deactivator. Sucks electron density out of the ring. And we say this is an inductive effect, just the same way an alkyl group donated electron density through a sigma bond. So let's put this on in the ortho position. And there would be a positive charge there, but then you get to move one of those electron pairs down, you get the double bond there. Putting it into the para position, so that they're not showing you all the resonance. But in the meta position, you can never form that double bond. But in the para and ortho, you get more delocalization. Just back up and look at more para than ortho. More para than ortho. I don't know, in my eye, I like the parallel symmetry of all this conjugation. You still have it all conjugated around this way. Maybe nature likes that, and that's why we get more para than ortho. The resonance effect. The lone pairs on the halogen can be used to stabilize the sigma complex by resonance. Chlorine is deactivator. So the transition state is higher than benzene, but the ortho-para positions, you can get this stabilization that you can't get in the meta. So many years ago when I was an OChem student, I got all this and went in, and I'm like, all right, I understand it. And then I took the quiz or exam. And so here's how you want to read this chart. I saw that this line was here, and then I said, oh, if it's deactivating, it's meta directors. It's activating, it's the other two, and then I missed that all of these were ortho-para directors. So this double line divides ortho-para from meta, but this line divides activating versus deactivating. As an OChem student, I didn't understand that the first go around until I got the exam, I quizzed back. Then of course I probably forgot until I taught OChem here. So someday when you have an exam and you can bring a card, you're probably going to want to have something like this on your card. So of course, that's a hint. Know which groups are activators and deactivators. Possibly more importantly, the line between meta-directing and ortho-para directing. And it's mainly the halogen. Now what if we have two substituents on a ring? The methyl group is ortho-para directing. This thing is meta. Well, meta to the nitrogen is right there, and that's ortho to this thing. And this thing, if it was para, there's already a group there. So you run this reaction, there's only one choice of what happens. You're going to put a nitro group right there in the ortho position. The directing effect of the two or more groups may reinforce each other. In that case, it's a simple process to figure out where the group goes. Now I have two methyl groups. So I look at this one, and here's the ortho, here's the para. Look at this one, here's the ortho, here's the para. And so it says here each group is ortho to one methyl and para to the other. This one's ortho to both, but it's kind of hindered, more crowded. So you probably end up putting one over here. I kind of think this is a typo. Oh, no, it's not. All right, so here's our ring, and we're gonna put a group on there. You can go here, which is identical to this position here. If you put it there, you could spin it around and draw this picture. The position between the two groups in position 1 and 3 is hindered. For substitution is less reactive. All right, we have an anisole that was activating ortho-para position. This group is deactivating, and this is a meta to this, and there's group meta there. So let's sulfonate this, and here's our two products. If directing effects oppose each other, the activator wins. The most powerful activator group has the dominant influence. Friedel Crafts alkylation. Last name of two fellows that figured this out. Remember when I'd say alkyl halide's the big building block? That's what you see here again. Here's an alkyl halide benzene ring. Use one of these catalysts and you can alkylate a benzene ring. synthesis of alky benzenes from an alky halide and a Lewis acid, usually aluminum chloride. You can put an alky group on a benzene ring. So the alky halide reacts with this Lewis acid, produces a carbocation, which is the electrophile. So we're going to use tetrabutyl chloride as our alky halide. Here's our aluminum chloride. And so this is the activation of the electrophile. This here is the electrophile. Pi bond electrons go after the electrophile. Here's our sigma complex. And so then we can imagine pulling off a proton. Those bonds jump back down. And we regenerated our catalyst and we get some HCl out of it. You can imagine this chlorine and the hydrogen that goes missing ends up as the HCl. So any way we can make a carbocation, we can probably make an electrophile for our electrophilic aromatic substitution reaction. Here's an alkene, here's HF. Looks like these electrons here grab this proton in a Makarnikov fashion. And here's our alky halide. For whatever reason, when we did the alkene chapter, we never made a alky fluoride we never fluorinated an alkene with HF for whatever reason. But they do this a lot at the refinery. They work with this stuff. It's real nasty and dangerous to work with. So here's our electrophile. It can do its thing, form the sigma complex, then fluoride can pull off that hydrogen, and we've done an alkylation. An alkene can be protonated by HF. This weak acid is preferred because the fluoride ion is a weak nucleophile. That's why we didn't make alky fluorides from alkenes in chapter 8. Doesn't affect the carbocation. We can take an alcohol and boron trifluoride, form a carbocation, and then that can be an electrophile. So the Fiedel-Crafts alkylation isn't perfect. The reaction fails if benzene has a substituent more deactivating than halogen. What are those? Probably the main thing to remember now is the nitro group, because in the future on a quiz or exam you're asked to synthesize some multi-substituted benzene compound, and you might have to you're going to have to pay attention to the order. Rearrangements are possible of your alky halide. I mean, if you don't mind the tertiary carbocation doing the thing. All right, then if you think about it, once you put on an alky group, the benzene becomes more reactive, so then you can get multi-alkylations. Polyalkylation can occur. So you might think to yourself, oh, it might be nice to make a benzene ring that has a 3-carbon chain on it. So you get yourself a 3-carbon alky halide and your catalyst, and you run the reaction, and you didn't get your nice 3-carbon chain. You got this thing here. So this is the rearrangement.